drive the robot.
Okay.
And then you have a sensor here so you can see, and a ground sensor position where he is on the ground.
Okay.
There are places where the robot will be crossing lines, taped lines, so he's going to know where those are at. We have 2 battery packs. There's one here that runs the upper works. There's another battery pack inside the brain which runs this, and that's the programmable part. The Samantha part, which is the Wi-Fi, is not here yet.
Okay.
Because that you can position in any place you need the Wi-Fi control.
What is this?
Servo controls will control all the servo motors that are in the upper works to make arms move, levers raise, gears turn. This is a DC motor control, so that's going to control these. The way this thing is going to turn is that one will slow down while the other one speeds up. And in the difference, then it turns.
Okay. And how...
These other wheels back here are kind of interesting because as it turns, look what that does.
Oh.
You have an axis going this way, but these guys spin the opposite.
Very
so they
cool.
can turn. We left our axles on the looser side so they don't bind. I made sure that there was clearance in there. Because if you tighten them up, it becomes resistance.
How long did it take to build this one so far?
If you add it up all the time, this took about 5 hours.
5 hours, wow.
That was because in the very first day when we started over here, putting these pieces on, actually, we started here with this piece. It was going in these boxes and going to find all this stuff. So it took time. That very first day, we learned something. We got to have somebody coming in here. We were using those bins we bought, and like they do in an auto assembly plant, pre-position stuff, where you got material feeding into the build. Well, versus sitting there, okay, we got to find this part. We got to find this part. That's my job now. I'm in here today until the robot build begins at 2:45. I'm going to have those parts ready to build that second robot already in the bins. So when they get in here, we go bins 1, 2, 3, boom, 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 and we build.
So you're going to have 2 robots?
Yes. This is the XR1. This is the experimental robot, the prototype.
Will the second robot look like this?
The automotive portion will look identical.
Okay.
To this.
What else would it have that this one doesn't?
It may be configured different on how they decide to pick up the balls. We already began looking at some ideas for picking up the balls.
Okay.
We were brainstorming in here on Saturday in the last hour about how the requirements of scooping up the balls. You can only store 5 balls at a time in the robot itself. And then it's up to you to figure out how the balls are raised and then how they're placed into various cans, plastic cans, varying heights. It has to autonomously go, and as you'll see later on, we build the field. And there's a field centerpiece, they call it. And the robot has to, by itself, then go knock out one of the kickstands, and all the balls come out, 144 of them, of 2 sizes. And it has to go and pick up all of those balls, and given so much time to put balls in these large tubes. Some of the tubes, you have to go and push them into various goal areas. You score points that way, too. So there's an autonomous part where the robot starts off on a ramp, goes down the ramp, and goes and you program it to find where it's at in the field and knock that kickstand out, one side or the other, to release the balls.
So it won't be remotely controlled?
It will be remotely controlled once the kids will, after there's like 2 minutes of autonomous control, then they take over and they run the robot. So there's different steps to that. That's where Samantha comes in, because that's Wi-Fi off the controllers. The controllers you could plug in but then you're only allowed about 6 feet of cord, and you're going to need more than that.
Oh, yeah,
So
okay.
you better have Samantha, your Wi-Fi connection, hooked up to your motor controls and your servo controls. So Samantha is not with the robot at the moment.
Okay. And this is simply a telephone wire? Telephone
Yes,
cable?
like a cable, hook up to the sensors to feed back into the robot. That's the brains.
This is standard Lego.
Yes,
work-
that was supplied by the Lego company. I put that battery pack in myself because when I took the back cover off, you could actually put batteries, 1.5-volt batteries in there. But they suggested, of course, the rechargeable one, and that's got a recharging port right there. That red and green lights let you know that it's getting low on juice, or you're fully charged.
Okay.
So that's right now. I don't really want us playing too much with this because I don't want to have this thing think that, okay, that's the biggest charge we get, and we go to 0. It might not go beyond that.
Okay.
Because that's the only problem with those type of batteries. They've got a brain to them. So I want this thing, before we even run it anymore, fully charge those batteries. Then,
And just only the kids worked on this model. You didn't do anything to this?
the only thing I did was simply hold. My hands became a fixture to hold some parts so the kids could put the screws on.
They put the
I
screws
put
on.
none of the screws on. They did it. All of the children who were in the class in this robot build, everybody built. Everybody turned screws for the first time. We wanted to see who liked doing that job and who didn't. And you don't know who your screw turners are until you get a chance. But everybody got a chance, and a lot of them liked it. Some of them didn't. They've got a lot of their bio papers that they're working on, and they're filling out their engineering reports. I've made some sheets that answer some of their questions. We went through basic electricity in a sheet that I gave them. And then some of the kids asked, Mr. Mike, how did they make these pieces? How was that made? They had no picture of it. So I went through books that I have on sheet metal forming, and then what a die and a press is. Because the die that forms these pieces can do nothing without the press. Otherwise, the die just sits there. See, and as you can see, there's one of the Lego pieces right there, one of those channels. That's how it would be made.
Very cool.
My first associate's degree is in tool fixtures and dies. That's for mass production. That's what you would need. And then they were asking about, a DC motor. So I gave them an explanation of a DC motor. And this is on a much larger scale, but that's the inside guts of a DC motor. And this is the basic principle of how it works. You've got magnetic field formed by permanent magnets. When you run a current through that wire, it now creates a different magnetic field. Opposing magnetic field, something's got to turn. And that's simply how that's done. And this, of course, is a more elaborate scale of a very simple idea. DC motors are inexpensive. They can be any size you want, from the giants down to little ones.
And could people at home build something like this?
Yes.
Where would you get these parts from?
Any hardware store. We were kids, we used to build them with nails. We'd wrap the wire around them, get a couple magnets on a post, and hook it up, and it would turn. We would support the nail,
Could you get instructions on how to build something like this online, or where'd you get instructions?
The instructions for this came in as lesson plans that we followed on a step-by-step basis. And here we ended up, with the basic bot.
It looks
See?
exactly the same.
Mm-hmm. This is, again, the end of the lesson. There's your base bot. Lesson 4 now is going to take you through various types of how to build arms and where to put servos And they gave us a lot of parts. We've got a lot of parts left over. And the kids were asking, Mr. Mike, why do they have all these extra Lego pieces, extra metal? It's because off of the extra metal and all the extra Lego parts is how our imaginations are going to be able to put these things together. And it's unlimited. We have, in essence, an unlimited number of combinations that we can come up with. The only limit being the number of pieces we have. There's like 4 times many more of these pieces left over.
So it's basically a more advanced Legos.
Mm-hmm.
Okay.
It's very much advanced Legos. If you wanted to order this for a son or a daughter, you'd be prepared to spend about maybe $400 to $900, and it's going to come in about 5 different boxes.
And you could build any kind of robot you want, basically.
Yeah, once you've got the base kit, like this build, and you build a couple of these robots with this type of things and you see how it works, then it begins to give you ideas. Well, what if we built the arm this way? You can try it out. It's almost at a point where it's unlimited. The only thing limited is your imagination and how many parts you've got left over in the box. You've got lots of parts. But this is going to be, like I say, the kids are coming up with a name for the robots, and I have my Mr. Mike tag on. I'm going like this, and they said, "Oh, we're not naming it Mr. Mike." But to keep them separate, I already bought the tape, and I'm going to tape to one. This is going to be the RX1, so there's no mistaking that the other one's the more competition bot, because they want to see a prototype bot and a competition bot from the 2 teams. One team is one bot, one team is the other. There's 2 robots. In other words, you get a chance to try out your ideas with the one, and the other one should reflect, the best of the best. And they'll both compete.
Yeah. How fast can this thing go?
I don't know yet.
Okay. And you could potentially build things for faster speed, right? Racing robots?
I don't know if you can. I don't know how these are geared. If you listen, you can hear the gears. So I don't know how they may have this set up for all power, which the robot will travel slower, but have a lot of oomph behind it. If they build it to go faster, well, it's like a teeter-totter. You go faster, you're going to have less power to move something. If you do it the opposite way, you end up with a lot of power but a slower speed.
Very cool.
When I worked on the M1 tank, the main shaft on that turbine engine turns at some 38,000 RPM. It goes through 3 torque converters before it goes to the transmission. At the final drive, you're down to 3,000 RPM, 1,500 horsepower. So yeah, that 70-ton armored vehicle moves out 45 miles an hour. That's a lot. That's fast for something that weighs 70 tons.
Pretty fast.
Elusive. Now you see it, now you don't. You try and target that, but it's moving around that fast.
That's top speed?
That's governed. If you took the governor off, you could go faster. But you might throw tracks. The track would literally come apart.
Oh.
Because it's just too much load and force. So they put a governor on it to slow it down.
What's a governor?
It keeps the engine speed not allowed to go beyond a certain point, no matter how hard you push down on the pedals.
Oh.
Governs the engine.
So it's like a fail-safe kind
Yes.
of deal? Okay.
Yes.
Very cool.
Because without that, you crank it up to 60, 70 miles an hour. The next thing you know, you're throwing a 3-ton track off the tank. Whoops. You wouldn't want to be in the way of that.
And those are metal treads on the tank?
Yes. Each track on an M1 tank weighs 3 tons. It's 6 tons of tracks. You wouldn't want to be around when that starts flying apart.
They also have tanks that are rubber tracks, too?
Well, there are pads on those. All of them have those pads. And the soldiers are able to remove every 3rd set to make what they call active or live track when they need to cross ground. They put the rubber pads on and ride them on the roads because you don't want to tear the roads up.
Right. All right. Well, thank you, Mr. Mike.
Yeah. Got to give our usual on-off switch to turn it on and off.
Ah, that's useful.
Yeah. But there was a young lady named Courtney, and her brother Brent stopped by. And Brent and Courtney started wiring.